So that is the first line of evidence. The Hubble constant, as the redshift tends to infinity, that is the scale factor, tends to 0. The Hubble constant at that time tends to infinity. The other line of evidence for a Big Bang comes from the evolution of the density. Considering the definition of the density parameter, we can write it for the present time and divide one by the other to find this relationship between the density parameter, the density, and the Hubble constant. Now we can write this in terms of the scale factor if we consider that, according to conservation of mass, as the universe expands, the density must decrease with the cube of the radius, and the radius in this case is the scale factor. Now if you write this in terms of the redshift, that is 1 plus z to the cube. So you can rewrite this equation then as omega over omega naught is equal to 1 plus z cubed h naught squared h squared. Now, if you put again on the left-hand side what you cannot observe and in the right-hand side that you can observe, then this becomes h omega squared is equal to 1 plus z cubed omega naught h naught squared. Now we can eliminate the Hubble constant from this expression with the expression we found for the Hubble constant. That is, if you square this and divide it by h squared, now plug this relationship here and you find omega over omega naught is equal to 1 minus omega naught times 1 plus z. Now if you solve this for omega, you find omega is equal to 1 plus z over 1 plus omega naught z times omega naught, which you can simplify to omega is equal to 1 plus omega naught minus 1 over 1 plus omega naught z. Again, in the right-hand side is the present, and in the left-hand side is any age in the universe. Now, there are two interesting results that you can derive from this equation. The first is that the sign of omega minus 1 does not change. It depends only on the sign of omega naught minus 1. The redshift is not changing the sign of this expression. That means that if the universe ever had omega minus 1 bigger than 0, it's always going to be bigger than 0. If the universe had omega minus 1 less than 0, it's always going to be less than 0. If the universe has ever been closed, it has always been closed. If it is open, it has always been open. The universe is either always closed, always open, or always flat. The last one is particularly interesting. If you have omega equal 1 at any time, then omega equal 1 at all times. Again, this is a statement of conservation of energy. Either the universe is closed, open, or flat. It does not change from being closed to being open, or from being flat to being open, or flat to be closed. Now, the second consequence that you can derive from this is, again, if you put the redshift equal to infinity, then you cancel the last term. If z is equal to infinity, then this term here cancels, and you have that omega, that the limit as z goes to infinity, as you approach the Big Bang, the limit of omega is 1. Now, this tells you something very important about the early universe. No matter if the universe is open or closed, the early universe was essentially flat. This last result allows us to simplify several equations in cosmology for the early universe by simply setting the curvature term equal to 0. So these are the two conclusions that we can derive from the evolution of the density. The sign of the curvature does not change, and the early universe is essentially flat.